Hello, everybody out there in YouTube land. This is Good Times for All, or Zachary Zabala if you prefer. In today's video, we're going to ask the question, trouble with Maxwell's electromagnetic theory. Can fields induce other fields in vacuum? Written by Ionel Dinu, a physics teacher. His information is right there. You can contact him. This was brought to my attention by this wonderful lady who goes by the name Fractal Woman here on YouTube. We will be covering this video right here. It's the last one that she uploaded, and she comprehends this stuff so well. She goes and does her own tests, makes her own observations, and questions when things don't act accordingly, and even looks at the bigger pictures. And in this video right here, she is going to... This just blew my mind. This is what I've been looking for the last month to try to share with you guys. And I can't thank her enough for sharing this. So please, at least go check out her channel and give her video a like. If you enjoy this, the link will be in the description. Without any further ado, here we go.
So today I want to complete the review of the paper by Ionel Dinu called Trouble with Maxwell's Electromagnetic Theory, Can Fields Induce Other Fields in Vacuum? So I think the main takeaway from the first two sections that I previously reviewed is that the question is, the operative question is, can a field generate a field? But I think the real question is, can a field exist without charges? Now, what are charges? Well, charges are, electrons and protons and ions, any unpaired charge or any charge with a so-called positive or negative charge. So these are unpaired charges that exist in nature. So can a field exist without charges? And in particular, can an electric field or a magnetic field exist without charges? So what do we know? We know that a static electric field needs charges. Without positive or negative charges, there would be no static electric field. Voltage can exist without charges. In order to get a voltage, you need charge separation. Electricity, current going through a wire, can't exist without charges, obviously. And we know that magnetic fields are generated by moving charges. So all experiments that have ever been done in the past actually, in fact, involve charges. So the creation of electric fields, magnetic fields, they all involve charges. So it does seem that all fields, magnetic fields and electric fields, cannot exist without charges. So the question, can a field generate a field? I'm going to say the answer to that question is no. So hopefully through the final review, the review of the last part of this paper, we can come to the conclusion that no, a field cannot generate a field. Charges need to be present even in vacuum. So in vacuum, what is a vacuum? A vacuum is a region of space that contains no atomic particles. So no atoms, no hydrogen atoms, no electrons, no ions. So vacuum historically is you pump out all the atoms and then you're left with what the ether is made of. And that is the direction that I'm taking in my research. So next we're going to do a little review of Maxwell's equations. So these equations here are the state of electrodynamics before Maxwell. So you have the first one here, Gauss's law, which is really the law of electrostatics. And then we have the next one, which he calls no name, but it's really Gauss's law of magnetostatics. And then we have Faraday's law, which is really the law of induction. And then we have Ampere's law here, and this is the one that Maxwell changed. So the set of equations after, so Maxwell changed the equations, they're exactly the same, except that Ampere's law has another term here. And it's this term here that gives us the idea, gives us maybe the false impression that an electric field, a changing electric field, can create a magnetic field. And this is what the next few sections we'll be talking about. Okay, so reading from Yonel's paper, he says, observe that Ampere's original law, which is this part here, which was a mathematical description of experimental findings relating the magnetic field to the current density, J, this J means current density, producing it, has been changed by Maxwell by adding a supplementary term to the right-hand side of the equation, which is this term here. Maxwell's addition of this term has received the name Maxwell's displacement current. Ampere's original law allows the calculation of a magnetic field produced at a point in space by currents flowing along other curves in space. It has experimental roots in Oersted's great discovery that an electric current produces a magnetic field in the space around it. If another term is added to this equation, it follows that the magnetic field can be produced also in this manner described by this term. Adding this term to Ampere's original equation is equivalent to saying that a changing electric field can produce a magnetic field. Maxwell's modification of Ampere's law by the addition of this supplementary term is not correct, according to Yonel and the information he provides in this paper. So why is Maxwell not correct? Maxwell is not correct for the following reasons. Number one, such an effect that a changing electric field can produce a magnetic field has not been observed experimentally. Therefore, adding this term, to Ampere's original equation is pseudoscience. To see how absurd the matters can get, observe that you obtain a magnetic field even if there are no electric currents at all. So for J equals 0, for current density equals 0, Ampere's law, modified by Maxwell, becomes this. Okay. Since the electric charges, static or in motion, do not appear in this equation says that a pure electric field, varying in time, can create a pure magnetic field. This is pseudoscience because experiments show that fields are created by charges. An electric field is created by a static charge, and a magnetic field is created by a moving charge. Every time there is a field, this field can be traced to an electric charge at rest or in motion. The equation above, however, implies that charges and currents are not necessary for the creation of fields, and that one field, a time-varying electric field, can directly by itself, without other means, without the aid or mediation of something else other than itself, create another field, a magnetic field. According to Coulomb's law, and actually I think what he means here is Gauss's law. I think he made a little bit of a typo here. And this, I just want to do a little aside here. I have a real problem with naming equations after people. I have a little bit of I'm going to call it a learning disability. I have a really hard time connecting people's names to physical laws. Now, I mean, this is, Coulomb's law is actually the force equation for electric charges. And so, but really, it doesn't matter what it's called. This is the law of electrostatics, and which is normally called Gauss's law. Now, if we just called it the law of electrostatics, I don't think Yonel would have made this mistake, because you should call the equation for what it is. Faraday's law should be called the law of magnetic induction. And, this law should be called the law of electrostatics. And divergence of B equals 0 should be called the law of magnetostatics. So I really wish that science would call things for what they are, and people like me who have a hard time connecting people's names to physical laws would not be so confused. So that's my little aside, and let's continue on. So according to Gauss's law, according to the law of electrostatics, the electric field can change in time if and only if the charge density changes in time. But this is not apparent anymore in Maxwell's modification of Ampere's law. Note that Faraday's law seems to indicate another way in which the electric field can be changed, but this is only apparent. As we will discuss later, Maxwell has modified Faraday's law by making the same conceptual mistake as he did when he modified Ampere's original law. For what Faraday observed through experimentation was that a changing magnetic field induces a current and not an electric field. So the mathematical rendering of Faraday's law is also questionable, and he will discuss it later. So let's move on. Maxwell's displacement current is not an electric current. If there are supplementary currents to be added to Ampere's law, and we will see later that one supplementary current must be added, these currents must be added as currents and not as something else, such as a varying electric field, because this is what observations show. Moving, changing electric charges produce a magnetic field around them. A current, more accurately current density, because that's what that J means, okay, current density, okay, is defined as, right, current density times velocity, so, or charge density. So this little p here, whatever the Greek symbol for that is charge density times velocity. So current density is charge density times velocity. So current is charge in motion. So how should Maxwell have corrected Ampere's law? It's one thing to say that a law is not correct. It's another thing to explain why it's not correct and to come up with a correct solution. And that's what Yonel does in the subsequent sections of this paper. So again, this was the state of Maxwell's laws, or state of the equations of electrodynamics before Maxwell, okay? So these equations represent the state of electromagnetic theory over a century ago when Maxwell began his work. They were not written in this compact form. I think Heaviside came up with this compact form, but their physical contents are familiar. Now, it happens that there is a fatal inconsistency in these formulas, and it has to do with the old rule of divergence of curl always equals 0. If you apply a divergence to equation 3, everything works out. Everything works out. The left side is 0 because the divergence of a curl is 0. The right-hand side is 0 by virtue of equation 2. But when you do the same thing with equation 4, with Ampere's law, you get into trouble. You get into trouble. So the left side must be 0, but the right side in general is not. For steady currents, the divergence of current density is 0. But evidently, when we go beyond magnetostatics, so this is fine for magnetostatics, okay, but when we go beyond magnetostatics, Ampere's law cannot be right. Of course, we had no right to expect Ampere's law to hold outside of magnetostatics. After all, we derived it from the Biot-Savart law. However, in Maxwell's time, there was no experimental reason to doubt that Ampere's law was of wider validity. The flaw was a purely theoretical one, and Maxwell fixed it by a purely theoretical argument. So how did Maxwell fix Ampere's law to conform to the continuity equation? The problem is on the right-hand side of equation of the previous equation, which is this one here. So applying the continuity equation in Gauss's law, the offending term can be written like this. So this term here can be written like this. So it might occur to you that if we were to combine this part with this part in Ampere's law, it would be just enough to kill off the extra divergence term, which is this term here. And then you end up with the modified Ampere's law. So such a modification changes nothing as far as magnetostatic is concerned, where the electric field is constant. So there's no change in the electric field, so this term would be zero. So we still have the original Ampere's law. In fact, Maxwell's term is hard to detect in ordinary electromagnetic experiments, where it must compete for recognition with current density. And that's why Faraday and others never discovered it in the laboratory. However, it plays a crucial role in the propagation of electromagnetic waves, as we will see in Chapter 9. In my opinion, in Yonel's opinion, there is a correct and honest way in which Ampere's law can be fixed and make it comply with the equation of continuity. It starts from the following idea. How must current density in the original Ampere's law be changed so that the curl of this equation is equal to zero, the curl of an equation is equal to zero? The change of current density can be made by adding another current density, so that Ampere's law becomes the following. So then the vector calculus identity used by Maxwell, which says that for any vector B, the expression, the curl of magnetic field, must be zero, leads to this the following here. So the equation of continuity, which he now exposes as being this, and if you want to look up the equation of continuity, I'm not going to go over it right now, but you can look it up, and you might want to do that before you continue on here. But so he's trying to conform to this equation of continuity, which is right here. So the equation of continuity and the above result then show that the extra current density that must be added to Ampere's law must be such that, okay, this new current, the divergence of this new current, is equal to changing charge density. So charge density changing over time, that's what this means here. So this expression shows that the additional J prime term depends on the time derivative of the charge density. Okay, it depends on the time divergence of charge density. So that's another way that charge can change. Charge can change by flowing through space, by moving through space, and charge can change by the changing charge density. So with this expression for J prime, Ampere's law becomes this. Okay, so a magnetic field can be created by current density, right? By current density, or it can be changed by changing the charge density in a region of space, and then the curl of magnetic field equals zero, as required by the vector calculus identity. So how is this modification different from Maxwell's modification? The above modification is different from Maxwell's in that Ampere's law still contains currents and only current densities actually, as observed experimentally. I consider it correct because no other physical quantities are added artificially, only currents, only changing currents moving through space and changing charge densities. Also observe that for vacuum, there are no charges. So at least there are no unpaired charges in a vacuum, and no current. So if there's no charges, there can be no currents, and there can be no current density. And so J prime becomes 0 because it depends on the existence of electric charges. Ampere's law for vacuum then becomes the curl of magnetic field equals 0, which is completely different from that obtained by Maxwell. So when charge densities are 0 in the original Maxwell's equation, then you get the curl of magnetic field is equal to the changing electric field, which has never been observed experimentally. It was just an assumption because of the mathematical gymnastics that Maxwell did to come to this conclusion. In Maxwell's modification of Ampere's law, this supplementary term is not left as above, but it is expressed further through purely mathematical manipulations. So Maxwell could have easily done this, but he did further mathematical manipulations to end up with this final term. So then Yonel goes on to describe this purely mathematical manipulation that he did, that he derived from the book Introduction to Electrodynamics by David J. Griffiths. So Maxwell starts from Coulomb's law, which is really Gauss's law, and I won't complain about that further, but Gauss's law, which is this law here, right? The divergence of electric field is directly proportional to the charge density in a region of space. So obviously, which he uses in the case for which there are charges. So obviously, if there are no charges, there can be no electric field. So, but Maxwell afterwards claims that the modified Ampere's law that he obtained through is also valid for vacuum, even though he gives no justification for why all of a sudden this equation is valid for the condition where the charge density equals 0. So Yonel goes on to reproduce this manipulation, which I won't go into detail about, but you can either look at the paper or you can press pause on your computer and just go through these points. But basically he starts with Gauss's law, and he ends up with this new J prime term, which he suggests is that a changing electric field can create a magnetic field. And so he went through this whole manipulation and put this version of his derivation into the equation. So instead of putting this part, which is the changing charge density, instead of putting this into the equation, where clearly there can be no changing charge density without charge being present, he put this part into the equation, which gives the false impression that a changing charge density is going to create a changing electric field. But Maxwell put this part into the equation instead of this part, and giving the false impression that a changing electric field can exist on its own in vacuum where there are no charges. And now looking at this more, with more clarity, it sounds kind of ridiculous. So the difference between Maxwell's modification of Ampere's law and the one which Yonel did is summarized below. Okay, so Maxwell's modification puts this into the equation, but he claims that there are, he doesn't realize that he is saying that the changing electric field is in a region of space where there are still charges, right? So this is not a pure electric field that exists all on its own. This is an electric field that is changing over time, right? Because the charge density is changing. And so this is what Yonel does, and I think this is the correct thing to do. So the difference between the two is enormous because in general, in physics, the equations connecting different physical quantities are interpreted phenomenologically. That is, they must correspond to effects observed in experiments. Okay, I'm going to say that again. They must correspond to effects that are observed in experiments. As stated above, Maxwell's version of Ampere's law implies that a magnetic field can be produced by itself by a changing electric field, which is true, but you can only get a changing electric field if the current density is changing. This has never been observed. A pure electric field has never been observed experimentally unless there are charges present. So for the vacuum, Maxwell's modifications of Ampere's law, and Ampere's law modified correctly, differ significantly, because in Maxwell's modification, if there are no currents available, there's no current density available, in which case the equation implies that a pure electric field can exist without charges, and that can create a magnetic field. And in Yonell's modification of Ampere's law, the curl of the magnetic field is 0 when there are no charges present. When current density is 0 and when charge density is 0, then the curl of the magnetic field is 0. So the difference is due to the fact that Maxwell was inconsistent in his calculations. He used Ampere's law with charges to modify, he used Gauss's law. See, that's why I hate names. I hate when people use names. Okay, I'm not going to go on about that, but I really don't like that because it's very confusing. So Gauss's law, he started with Gauss's law where there are charges to modify Ampere's law, and then claimed that the modified Ampere's law obtained from it is valid in vacuum where there are no charges. In fact, this claim cannot be true because if there are no charges, then Gauss's law becomes the divergence of E equals 0. There's no electric field and cannot be used anymore to find the expression to find this expression. Okay, it cannot be used. And so this is the flaw. This is the flaw that has created so much confusion over these years and given the false impression that a pure electric field can create a pure magnetic field, and pure changing electric field can create a magnetic field, and vice versa. So this is the source of the problem. Okay, so going back to what experimental evidence say, Ampere's law states that there must always be electric currents to produce a magnetic field. Even if original J is 0, it is the supplementary current of J prime not equals 0 that produces a magnetic field. This supplementary J prime term is produced through a changing charge density, right? Changing charge density right here. The equations always link fields with charges, producing them, and never omit them as important intermediaries between fields. The correctly modified Ampere's law does not predict absurd, never observed phenomenon such that, according to which a magnetic field can be produced by a changing electric field. Even if there is an equality of magnitude between J prime and the electric field. Okay, so obviously this J prime term is equal to, proportional to the changing electric field. This does not mean that a changing electric field can be replaced in the equation where J prime should appear. Okay, so basically a changing electric field can only be produced by charge density changing, obviously, in retrospect. So as a conclusion, Maxwell is not correct because in science, the equations we write should not be correct only because they're dimensionally and quantitatively affect but they must also correspond to observed phenomenon in experiments. Substituting this term for J prime in Ampere's law, although correct mathematically and dimensionally, is not correct phenomenologically, because the interpretation of the law thus modified leads to absurdities not observed in the real world. Okay, not observed in the real world. So then Yonel goes on to do a little kind of a thought experiment to show that. So he says there are many situations in physics when we replace physical quantities in different equations and obtain other equations that are correct dimensionally and quantitatively, and use them to calculate unknown physical quantities. So I really like what he did here, but I'm not going to review it because it's going to take some time. So he gives a little example here about how we can make a false interpretation from an equation that was derived mathematically correctly. So what I'm going to do is I'm going to give you just a simple, this is equivalent to saying something like, if there's smoke, there's fire, therefore when there's fire, there's smoke. Okay, and that is completely wrong. I spend a lot of time on the beach, and my husband and I, we make fires on the beach all the time, and sometimes if your wood is really clean, if you have really good wood and it burns very cleanly, there is no smoke. So you cannot say when there's, if there's smoke, there's fire. That's always true, because how do you create smoke without creating a combustion of some sort? So when there's smoke, there's fire, but that doesn't mean when there's fire, there's smoke. And this is sort of the thought experiment kind of way of looking at the mistake that was made by Maxwell. He said, when you have changing charge density, then you have a changing electric field. But that doesn't mean a pure changing electric field can exist on its own and create a magnetic field. So, I thought that was a nice, more simpler analogy to what happened with Maxwell. But you should also read this section of the paper, because this is another great example of how you can make a phenomenological mistake, but the math can be right. So I'm going to leave it at that for now. There's one more section of the paper that I still need to review, but I think this is enough information for one video. I think we can now answer the question, can a field generate a field? And I think we can safely say that the answer to that question is no. Not only that, but it's not necessary for that, because the experiments show that static charges create static fields, moving charges create magnetic fields, and moving magnetic fields cause charge to move in a current. And that's going to be the subject of the next and hopefully final section of this video series. So I hope everyone's doing well, and I hope I did this video. I hope I did Yonel justice by making these videos. And ciao for now.